Hey guys, I hope all of you are having a great conference. So given that this is a lightning talk, we have only 15 minutes and a lot of ground to cover. I'm going to speed run through a bunch of slides. With me today, I have Thomas from Autodesk, where we are going to talk about what exactly Metaflow is. If you are curious how we got started with the project, how does it relate to Ray, some of the interesting use cases that it services at Autodesk. And then if you have any questions, both of us are going to be around at the end of the talk to take those. So the title of our talk is Using Ray with Metaflow. So I'll spend the first 5 minutes just introducing what Metaflow is all about. So a few years ago, me and a bunch of other folks at Netflix, we were basically grappling with this problem that how do we support all the booming data science, machine learning, AI use cases at Netflix? And of course, now we sort of like live in a world where almost every single company that you can think about is investing in AI and ML. But if you sort of like go back, even sort of like 5 years ago, there was an open question: what does a machine learning platform look like? And I thought that maybe sort of like for this lightning talk, it might be useful to share what our mental model was, how we went about thinking about that problem, rather than sort of like going into the minutiae of what Metaflow is. So you can imagine if you are, let's say, if you are a data scientist or if you support data scientists or machine learning researchers in your organization, then at the end of the day, what they're tasked with is there's a business problem, and they have to optimize for some business metric or sort of like deliver some revenue outcome. And that business problem is usually predicated on access to some data, analyzing that data, and maybe building a machine learning model, a machine learning system, so that then you can actually see sort of like some growth in the business. And that's where your data scientist comes in. They usually sort of like start out with some sort of IDE, maybe a Jupyter notebook, maybe a VS Code editor, Vim, Emacs. They're like all sorts of flame wars that end up happening. And then the very first thing that they have to sort of like deal with is, where is my data? How do I get access to my data? Maybe you have like data warehouses, data lakes, data swamps. I mean, like plenty of buzzwords around, but by and large, it's very likely that if you're thinking about building a machine learning platform, you have a good handle on what your data looks like and how people are going to access that. But then very soon, the next question that sort of like comes up is that, okay, now we have access to this data. Maybe we can access this data on our laptop. But what happens when this data doesn't fit on our laptop? Or for security reasons, what if this data can never sort of like hit our laptop? How do we run any kind of compute in the cloud? And of course, this compute also comes in a variety of different shapes and sizes. You may want to process small data. You may want to process medium sizes of data. You may want to process large data, where you may start thinking about distributed training. And now all of a sudden, your data scientist who understands data science inside out, now they have to start thinking about infrastructure concerns as well, right? Like, I mean, creating gang clusters, managing those, that's not sort of like really straightforward even this day and age. And then you sort of like get to this universe where they may not have one workloads, but they may have multiple workloads. They might be doing some data processing. They might be training some models, running some inferences. How do you then stitch together these workloads? That becomes another big pain point, and that's where sort of like your workflow orchestrators, like the Airflows and the Daxters of the world, sort of like start coming in to picture as well. And then you start to get into some of the issues that are more endemic to machine learning as a concept, right? I mean, at the end of the day, nobody wakes up and decides that, hey, this is my model. I'm going to write this code, point it at my data set, and the model that comes out is going to be the very best model. There's a lot of iteration, a lot of experimentation that's involved. And how do you basically then ensure that as your users are doing work, then without sort of like any significant cognitive overhead, people are able to actually sort of like maintain some sanity and figure out what is the work that they are doing, what are the models that are being trained, are they actually sort of like worth their salt, should you swap them with sort of like what the production models are currently sort of like in use. And then, of course, like just by training a model, the work is not done. You have to figure out how to deploy those models depending on the use cases that you're involved in. These could be really small models that might live on your cell phone. These could be really large models that might require bespoke deployment strategies, as well as everything sort of like in between. And then, of course, like as a data scientist, of course, you also have to worry about that. I think there's sort of like classes of organizations. Some organizations who would want to sort of like, let's say, have a data scientist just think about, let's say, a problem, prototype some straightforward solution, and then pass it on to, let's say, an ML engineer or a team of software engineers who are then sort of like productionizing that model. But then a lot can get lost in translation. And then the goal sort of like then becomes that, okay, can you really make a data scientist a full stack data scientist and end-to-end data scientist so that they can really sort of like own their destiny from thinking about a business problem to delivering a machine learning system end-to-end? And of course, there's still sort of like the open-ended question that what is your model actually doing? How you are actually training this model? Are you using PyTorch, TensorFlow? How are you thinking about features? How are you thinking about your neural networks? All of that sort of like comes into picture as well. And luckily, this is one thing that they may have gone to school to study. They have a natural aptitude for modeling, but then everything else that we see sort of like below the stack is pure implementation detail that ideally a platform should take care of. And that's where basically Metaflow comes in, where the perspective is that can we basically take an opinionated approach around how data is accessed, how compute is instrumented, how people think about orchestration, versioning, deploying these models in such a way that their freedom of choice when it comes to practicing the kind of machine learning that they want to do is entirely preserved. And now, of course, we are at the Ray Summit, so let's talk about compute, let's talk about modeling. Now, from a machine learning researcher standpoint, of course, we wouldn't ever want to go to a machine learning researcher and say that, hey, you're only limited to specific kinds of training libraries, right? Like, it would be really stupid of me at times if I go to a data scientist and tell them that, hey, you can only use Ray or you can only use deep speed. I mean, we wouldn't ever expect them to come back to us and say that, hey, your data needs to be stored this way or like deploy Kubernetes in this specific way. So how do we separate out these concerns is always sort of like an interesting thing for us. And then as a platform engineer, as an infrastructure engineer, what I do really care about is how can we ensure that compute is plentiful, it's cheap, it's easily accessible. And on that front, just to give you a quick overview of how Metaflow sort of like works is, it's a very Pythonic interface that is driven by these decorators. So you can imagine sort of like, you can see in your screen, we have the Kubernetes Ray and the checkpoint decorator. And in this example, what's really happening behind the scenes is that a data scientist is writing some code, dropping some decorators, and in this case, these decorators are indicating that, hey, this train step, which is a Ray job, it needs to run on a gang cluster with 8 nodes. Each of those nodes by themselves need to have 8 GPUs and maybe 64 gigs of RAM, and it needs to be set up in such a way that we can run Ray jobs. You can swap it out for MPI, Torchon, Deep Speed, whatever distributed training framework you would want to care about. And then behind the scenes, Metaflow will take care of actually instrumenting that cluster for you. It's going to be an ephemeral cluster that will sort of like bring in and then sort of like tear it down. So that now as an end user, as a data scientist, you are completely insulated from any of the implementation details of these underlying frameworks, which by themselves can be sort of like really complex. I know I'm sort of like way over time, so I'll hand it over to Thomas, who will talk about how they have been using this setup at Autodesk. But before I leave you, of course, if you decide to take a look at Metaflow, you wouldn't be alone. Very likely that your favorite streaming services, your favorite food delivery apps, doctors, banks, they're all using Metaflow behind the scenes to power your day-to-day experiences. So over to you, Thomas.
Thank you, Savin. Great to be here. As you can tell from my accent, I'm from the UK. My body clock is telling me right now it's bedtime, so I'll try to be coherent, but I'm feeling a bit sleepy. So yeah, as Savin mentioned, I work at Autodesk. Autodesk is a design and make company. We make products ranging from media entertainment. These are like used by artists to make animated movies using 3D Studio Max and Maya, all the way through to architecture, engineering, and construction, where we make products for civil engineers and architects to build skyscrapers. And at Autodesk, we're well aware that AI is a very powerful tool and has a good place in our products for automating tedious workflows and generally increasing the leverage of our users, allowing them to do a lot more sort of things with their time. And so to that effect, I work in the research team, and we build models in an AI lab. And I'm working currently on data pre-processing. This is a challenging topic as we're working with unstructured data. It's spatial data, geometry data in the form of point clouds, meshes, or BREPs. This is a boundary representation model. This is a thing used in CAD for constructing geometry. And we're working with large data sets, tens to hundreds of terabytes in size. And once that moves down a pipeline and fans out with feature extraction, we can reach petabyte scale quite easily. We also have the challenge of then running through quite expensive calculations. So dedupe is quite expensive. And finally, curating sort of incremental data sets that are split for our ML team to use. So train, test, and validation splits. Now, the main challenge is we're using Ray data, but we've got very long-running jobs. We've got jobs that could run for days. And even with very large clusters, 4,000, 8,000 CPU clusters, that can still take a very long time. And as a result, we need to break up the problem into smaller batches. And that's where Metaflow came in, because we needed to effectively break up the problem and orchestrate over these very long-running workflows. So to give a little bit more further context, we have an AWS-based infrastructure. We have a managed infrastructure team that give us a interface into an account using SageMaker Studio as the primary ingress point. And in terms of how our Ray setup is currently configured, we're just using the VM launcher, although we have other teams using also Ray. So we still have access to all of the nice features of Ray, like the Ray dashboard. So we're able to proxy out from SageMaker Studio the dashboard port so that we can visualize the state of our cluster. So the general idea behind this orchestration approach is to just wrap our Ray jobs, our Ray client submissions within Metaflow steps, and then let Metaflow handle the orchestration and the construction of the DAG that makes up that workflow. And as Savin already alluded, the syntax for constructing Metaflow flows is really pleasant. You have a Pythonic class inheriting from FlowSpec, and then you have these decorators which define sequences or nodes in your graph. And the general idea being that you wrap, potentially, your job submission to Ray. So initially, we explored using a very fine-grained ephemeral cluster structure where we had a cluster for every single step, every batch step. And while this does nicely isolate concerns, allows you to tag resources really easily, the challenge is that sometimes it can be hard to debug, it can be hard to understand the overall state of the cluster or the overall flow, let's say, and how all those clusters are using resources in an aggregate. And so, yeah, as you'll see on the next slide, we have a slightly simpler approach now. One other thing I will mention is that when you're using orchestrators, you do need to be careful that if you use things like the Ray dashboard attached to forward a port to access the Ray job API, that is obviously forwarding a port. And if you have multiple logical tasks on a single physical machine where you're sharing the OS and the network ports, they can collide. So the solution is quite simple, actually. We have instead suggested to have just a single heterogeneous cluster which has multiple different worker types. As in our particular workflows, we're using various different specialized environments. These could contain rendering environments using OpenGL. They could have specialized geometry kind of kernels that we run that all have very specific requirements to run in them. And in terms of job submission, we're using kind of the other alternative way of submitting jobs, which is to instead bundle up manually the job code you want to run, rsync it onto the cluster, and then from the head node, run Ray exec on that code. So kind of in summary here, the code now expands out slightly more. So when you're at the client side in Metaflow, we're effectively saying, hey, here's a key which is stored in Amazon Secrets Manager to connect to a given cluster. And then we're saying, hey, here's some code to bundle up and send across onto the head node before executing these given commands on that node to trigger the job. So this is now where Metaflow gets interesting for us. We can use the orchestration tools like for each to dynamically fan out and run all of our batches. We can also take advantage of the fact that whilst it's nice to have the kind of canonical graph of execution being this single fan out that shows what we want to run in parallel, you don't want to overwhelm your cluster with a sudden glut of many, many jobs being submitted concurrently. And so at the Metaflow level, you can limit or throttle the amount of jobs being submitted by using the num workers argument, which effectively Metaflow will then limit the number of concurrently executing steps at any one time. And so here's just an example of that syntax now growing out a bit more with the idea of defining an array of batches that then fan out over a for each command, so batch extraction runs in parallel, and then finally the fan in join happens. Something to mention I really like about Metaflow is the ability to cache metadata or artifacts inside of the flow spec, and then this is actually cached and stored on S3 and pickled by Metaflow. So in the future, or you can sort of look back to that job and you can access historical artifacts. So at the top level, this shows you what's actually happening. We look into our overarching kind of workflow, and we can see an execution graph which shows all of the different concurrently executing jobs. It shows their sort of overlapping concurrency. And if we wish to interrogate a given task, we can click on, zoom into that, and we can see the standard output from the Ray client that's monitoring that job. So looking forward to the future, we have, we'd like to start using the Metaflow Kubernetes runtime, which is on top of Argo workflows. This allows more interesting event triggering patterns. So you could potentially have cyclic workflows or event triggers such as GDPR deletion requests that trigger a workflow. So yeah, I'm afraid that's all we've got time for in this compact lightning talk format, but if you folks have any more questions afterwards, feel free to come and grab me, and it'd be good to talk more about orchestration. Thanks very much.